All right, in this podcast, we're going to go over some things about solutions. All right, let's start off with what a solution is. It's a homogeneous mixture where the physical properties are dependent on the concentration of the solute and the strength of the interactions among the particles of the solute and the solvent. So a solute is going to be the dissolved substance. It's whatever is being dissolved. So it's the salt in the salt water, or it's the sugar in, a Coke or something, or the carbon dioxide that gives us the carbonation in a soda. Solvent is the other part of a solution. It is the dissolving medium. So it's what's actually doing the dissolving. So it's like water in salt water or water in soda. Water is a very, very, very common solvent. We actually call water the universal solvent. All right, here's a molecular diagram, kind of gives us a little better picture. So you see the solutes are the little particles, like perhaps salt, that have been dispersed and dissolved in the solution. Solvent is the medium in which the solute was dissolved. All right, now understand that solutions can come in the form of solids, liquids, and gases. So this one over here, salt dissolved in water. This one is what we typically think of a solution. We think of a liquid, but we can also have a gas solution, such as the air we breathe is a solution of gases. It's a mixture of a bunch of gases. And also solids, so alloys or a mixture of metals can also be considered a solution. All right, so solutions can also have various solutes. So for liquid solutions, your solute could be a gas like CO2 over here in a soft drink, a liquid like putting acetone in water, or a solid like trying to put some sort of salt or ionic substance in the water. All right, do all solutes dissolve? No. Some solutes do dissolve. We refer to those as soluble. So if they dissolve in water, they are soluble. If they are insoluble, it means that they do not dissolve to a large degree in the solvent. All right, so how do we know if a solute will dissolve in a solvent? This all depends on the strengths of the interactions, or the IMFs, between our solute particles, the interactions between the solvent particles, and the strength of any interactions that could occur between the solute and the solvent. So particles of a solute are going to dissolve if they are more attracted to the solvent particles than they are to themselves. Okay, so they're going to want to basically go with whatever is the strongest interaction. So if they interact stronger with the solvent, they will dissolve. If they interact more with each other, then they will not dissolve. And we often refer to this little general rule of like dissolves like. So charged things tend to dissolve other charged things. Non-charged things tend to dissolve other non-charged things. All right, now some solutions do contain what we call electrolytes. Electrolytes are salts or molecules that split into positive and negative ions in solution. So salt, NaCl, is a great example of an electrolytic solution. Non-electrolytes are compounds that do not dissociate into ions. Remember, ions means charged in solution. So like sugar or sucrose is a great example. We do have the individual sugar molecules in here, but they are not breaking apart into ions. So it's a non-electrolyte solution. Which solution do you think will conduct an electric current? Hopefully, you're going to tell me it's going to be the electrolyte solution. So the one that's got the positives and negatives, it conducts electricity very well. All right, so commonly these two terms are confused. So we have dissociation and solvation. So dissociation is the splitting of an ionic compound into its component ions when dissolved in water. So basically think like reverse swap and drop here. So if I had my NaCl solid, when you put it in water, it breaks into Na plus and Cl minus. Only ionic compounds are going to be dissociating, okay? So covalent compounds do not dissociate. All right, now solvation is kind of the next step in the dissociation process, where your water molecules surround the positive and negative ions that you got from the dissociation, and they're going to surround the ions in a specific way because water is what we call polar. Polar means it has a partial negative and partial positive portion of the molecule. Now, I do want to point out that other things can experience solvation besides ions or ionic compounds. For example, sugar or sucrose is a polar molecule. So water molecules, which are also polar, will surround sugar molecules, but sugar molecules do not dissociate. All right, here's a little diagram of dissociation and solvation. So dissociation, you see we got our salt molecules, and they're breaking into the component ions when dissolved. Solvation is when water molecules surround the ion from the dissociation in a specific way. So here you see all the oxygens on the water molecules are pointing towards the sodium. All right, so what are these steps in solution formation? All right, first you have to have dissociation of your solute or breaking of IMFs if you don't have an ionic substance. Then the solvation of the solute occurs. So the water molecules begin to surround your solute in a specific manner. And then we have diffusion. So basically it becomes evenly dispersed throughout the solution. So why do some things form mixtures or solutions when added together and others do not? This all has to do with the types of interactions between solute particles and solvent particles. Again, just to reiterate, the solute is going to interact with whatever has the strongest attraction to itself. So if it has a stronger attraction to the next solute particle, it's going to remain undissolved. If it has a stronger attraction to the solvent particle, then the substances will mix, okay? Now, we see this commonly with like oil and water and different kinds of salts and such. So why is water so great at forming solutions? It's because water is polar. No, not like polar bear, like polar molecule. So polar means that the molecule has partial charges on it on different parts of the molecule. So for example, on our water, oxygen has a slightly negative charge, and my hydrogen side has a slightly positive charge. So because of this, it is attracted to ions or other polar molecules of the opposite charge. So the negative part of this water molecule, this oxygen, is going to be attracted to, say, a positive ion or the positive part of another polar molecule. So these partial charges allow water to interact very strongly with many solutes. Because water has that partial positive, partial negative, it interacts very well with ionic solids, and other polar molecules. So again, remember, like dissolves like. So polar dissolves polar or charged things. Nonpolar, which means that there is no partial charges within the molecule, only want to dissolve other nonpolar things. All right, so what about oil and food coloring or water and oil? Why don't these things mix? So if you had vegetable oil and water, you would notice that they form two distinct layers. This is because water is polar and vegetable oil is nonpolar. So they don't interact strongly together. This one, oil, it has no charges. Water has our partial positive, partial negative charges. So they don't interact very strongly together. They would rather interact with their own molecules. So oil would rather interact with other oil molecules. Water would rather react with other water molecules. All right, and just a little chemistry humor for you. So you see we have Mr. Polar Bear down here, and looks like we got like a brown bear or something up here. And Mr. Polar Bear, he is looks like he's in a river, and he's saying, "Help, help, I'm dissolving." And then Mr. Brown Bear says, "But bears are insoluble." And Mr. Polar Bear comes back, "That's easy for you to say. You're not polar."